Condensation is one of the key processes that leads to precipitation. So it's important to understand how condensation occurs and what some of the underlying principles are that predict when condensation is going to happen. Here are some questions. First, what is relative humidity? Second, what is the relationship between relative humidity and temperature? Third, what does the dew point represent? Well, the reason that condensation is important is that precipitation requires several conditions to occur. First, we have to have a humid air mass, which means it has to contain some water vapor, and that air mass has to be cooled to the dew point temperature in order for condensation to occur. Second, we have to have particles present, condensation nuclei, to form drops on. Third, finally, in order for precipitation to occur, the raindrops have to have sufficient velocity to reach the ground before they evaporate. And finally, for snow, only a few kinds of freezing nuclei lead to ice crystal formation. This is particularly important when we start talking about snow making and cloud seeding. So what is relative humidity? Relative humidity, often represented by the symbol W, is the ratio of actual vapor pressure, here the symbol EA, to the saturated vapor pressure. Let's call this E star. The saturation point for an air mass differs with temperature, and relative humidity at 100% represents a saturated air mass. That's as much water vapor as an air mass can hold or an air volume can hold at a given temperature. Relative humidity is dependent upon temperature and the amount of water vapor present in the air. What is the dew point? The dew point is the temperature to which air has to be cooled to reach saturation at a constant pressure. The dew point temperature determines if the condensate, or the condensed water, will be water. Here the dew point has to be greater than 0 degrees centigrade, or freezing, or ice. There the dew point is less than or equal to 0 degrees centigrade. Here's a graph of the dew point, a line of the dew point at different vapor pressures with temperatures in degrees centigrade. The blue line represents the point at which we have 100% saturation of the air mass, such that then condensation will occur. The little elements off to the left show the difference between relative humidities that are less than 100%, and then by cooling down an air mass, achieving 100% relative humidity with the same amount of water vapor in the air volume. We can estimate the dew point from a couple of different relationships. The bottom one, E star, is equal to 0.611 times the exponential function of the quantity 17.3 times temperature divided by temperature in degrees centigrade plus 237.3. The top one represents the dew point line itself, which is the relationship between the actual vapor pressure, not the saturated vapor pressure, but the actual vapor pressure, through this function on the right-hand side of the equation that has on the left-hand side TD. This is dew point temperature in degrees centigrade, and I'll show an example of that. TD is our estimated dew point. EA is our actual vapor pressure, the vapor pressure exerted by water in kilopascals. EA is the relative humidity times the saturated vapor pressure. Remember, relative humidity is expressed in percentage or in proportion of complete saturation. And E star then is the saturated vapor pressure as predicted by the equation immediately to the right. Let's estimate the dew point with calculations from the Valley Road Weather Station for Washoe, ET. In order to get this information, we go to the Western Regional Climate Center's website, go to Projects and Research, then Data Projects, and look at the Washoe Evapotranspiration Project. This site provides hour-by-hour summaries of climate and weather data, and the data can be used to calculate the dew point for existing conditions. So let's take a look at the dew point on 9/6/12. And then we'll be using the average data reported for the UNR Washoe ET station. The information that we need in order to calculate the dew point includes the relative humidity. Here on the 6th of September, it was 55%. The air temperature, the average air temperature on the 6th of September was 70 degrees Fahrenheit, which is equal to 21.1 degrees centigrade. We use that information to solve for the saturated vapor pressure at that temperature, and again in degrees centigrade. E star then is equal to 0.611 times the exponential function of the quantity 17.3 times the temperature, which is 21.1 degrees centigrade, divided by temperature plus 237.3. We then estimate or solve for the actual vapor pressure by multiplying E star, which is 2.51, times the decimal representation of the relative humidity, which would be 0.55, and we calculate that as 1.38 millibars. And now we estimate the dew point temperature by putting it in this equation, which is the dew point temperature is equal to the log of the natural log of the actual vapor pressure plus this constant 0.4926, all of that divided by 0.0708 minus 0.00421 times the log of, again, the actual vapor pressure. If we carry that out correctly, we find that the dew point temperature is 11.7 degrees centigrade or 53 degrees Fahrenheit. On the website it's reported as 50 degrees Fahrenheit, and the discrepancy between our calculation and that reported on the Washoe ET website is likely due to the use of our use of averages to do these calculations. What's the significance of this? It's when an air mass reaches dew point, vapor can condense to liquid. It's not the only condition that needs to be met, but it is one of the key ones. The air mass has to be cooled to the point where water vapor can condense, where our relative humidity is equal to 100%. And the significance is that when air masses rise, cooling occurs. And when cooling occurs, we may reach the dew point. The rate of change with temperature, or temperature with elevation, is one factor that produces condensation, and that can lead to precipitation. So again, remember, reaching the dew point is not the only factor that generates precipitation. But as an illustration of this, for the example that we just used, our temperature was about 21.1 degrees Celsius, which, given the dew point curve, lies here in an area where the air mass is unsaturated. The boundary at which we begin to see saturation is indicated here by the blue line, but we're in this blue zone in which the air mass is currently unsaturated. On this side of the curve, the air mass is saturated. So in order for condensation to occur, the air mass has to be cooled from 21.17 degrees to, as we said, about 11 degrees centigrade to reach the outer envelope of the zone in which the air mass is saturated. So back to our questions. What is relative humidity? Relative humidity represents the degree of saturation of an air mass. The bounds of relative humidity are 0 to 100%. At 100% relative humidity, the air mass can no longer hold any other water vapor. It's completely saturated with respect to the amount of water vapor that it can hold. and also relative humidity, is usually expressed as a percentage, but in the equations that we used, we're using the decimal equivalent of a percentage, or a proportion. The range of relative humidity when it's used in this way is between 0 and 1. What's the relationship between relative humidity and temperature? As air masses increase in temperature, if they retain the same amount of water vapor, the relative humidity goes down, and that is in part because we can put more water vapor in warmer air masses. So relative humidity is partly determined by the temperature of the air mass, as illustrated by the equations that we use to do the calculation. And what does the dew point represent? The dew point represents the point at which the air mass is completely saturated with respect to its capacity to hold water vapor.